So let's take a look at this little activity here. Okay, we're going to take a look at this function. Okay, we don't have a graph, right? We don't know exactly what it looks like, so it's going to be a little bit different to figure out what limits are for this graph. Okay, so first let's talk about the domain. How do we figure out the domain of a function?
Well, graph.
Okay, so like, what is domain? What does that even mean?
Is it how far all the x values?
Right, yeah, it's just all the x values that it reaches. Right? So if we don't have a graph, right, there are a couple of things that we can take a look at. Okay, so in this example, we have a rational function, right? A polynomial over a polynomial. We know that polynomials are defined everywhere, right? Their domain is all real numbers. But if we have a denominator, what do we have to look out for? Divide by 0, right? We can't have any places where the denominator is equal to 0. Okay? The domain, or that value will not be in the domain of this function. So what value would make the denominator 0? 4. So the domain of this function is everything except 4. All real numbers except 4. There are a couple of different ways we could write that. We could write that in set notation or in interval notation.
She's talking about when you do all real numbers. Yeah, there's a reminder that that's
all real numbers. Okay, so there are a couple of different ways to do this. The way that I actually prefer and the way that you're going to see it more in your textbook is interval notation. Okay, so the way that we can say that is negative infinity up to 4, not including 4. You remember the difference between the parenthesis and the bracket?
Bracket is including parentheses.
Right, parentheses. So parenthesis here means not including 4. And then we can say union 4 to infinity. Okay, this is the way you're going to see it written more often. Okay, we could also say, we could also do set notation and say x such that x is part of all real numbers, but x does not equal 4. That would be another way to do it. Okay, but this is the way that you're going to see it more often, okay, in interval notation. So we know, we don't really know exactly what the picture of this graph is, but what we do know is that 4 is not included on the graph. Right? That's what we know so far. So let's try to figure out what that limit is by using a table. Okay, we can't just figure out what the limit is by plugging in a value. Right? If I plug in 4, I get an undefined value. Okay? Now, just plugging in a value is going to be a strategy that we use sometimes. Okay, because we talked about graphically, we have some function, and I want the limit as x approaches 2. Well, if that value is part of the graph, we can just plug it into the function and say, well, if the function equals 1 there, then the limit also equals 1 because it's defined there. It's a part of the graph. We also looked at examples, where there was a hole there, where we couldn't just plug in the number. Okay, that's what's going on here, right? We can't just plug in 4 because we get an undefined value. So what we can do is make a table, okay, and figure out values that are really, really close to 4, okay, and see what value we're approaching. Okay, so take a minute here and plug in these 6 values into the function. Okay, plug in 3.8, 3.9, 3.99, 4.01, 4.1, and 4.2 to figure out what value, what y value we're getting really, really close to as we get closer and closer to an x value of 4. So I guess as a little aside here, how are you guys doing this? How are you figuring out each of these values? Are you typing in the whole function every single time? Okay, good. Okay. So if you plug that function into, y equals once, then you can go get some stuff up from last year. Okay, if you plug that function into y equals once, okay, then you can just go to value, get those 6 values pretty quickly. And so, what is the function? Square minus 2x. So if we do that, we could even graph it, and then we can get the value. You guys all know where value is. Go to second trace, values the first option. So then you could just type in the values that you want. So we're at x equals 3.8. I get a y value. I guess I've got it set to just give me fractions. Okay, 29/5, or in terms of decimal. So in terms of a decimal, so what did we get for the rest of those values in the table here? So, what value are we approaching as we get closer and closer to 4? 6, right? Okay, so how would we write that? Okay, how would we write so we want to say limit of f of x as x approaches 4. And we could even specify, we could say as x approaches 4 from the left, and then separately as x approaches 4 from the right, and then separately as x approaches 4. Okay, but since we already know that we're approaching the same value from both sides, we can just write the two-sided limit. And we can say the limit as x approaches 4 of f of x is equal to 6. Okay, so as we get closer and closer to 4 from both sides, we're approaching a y value of 6. Okay, so we wanted to plot that, which we already did. Right, so if I plot that here on the graphing calculator, it's just a straight line. Let's talk about this for a second. Why does that rational function just become a straight line like that? Fine? Right. So if we go back up to that function, okay, x squared minus 2x minus 8, we can simplify that some. Okay. The numerator, factor, what would that factor into? Wait, what is it? It's not going to be plus 4 and minus 4. Yeah. I think it's going to be x minus 4 and x plus 2. Right. Two numbers that multiply to negative 8 that add to negative 2. Negative 4 and positive 2. Right, so those x minus 4s then cancel out. So what we end up with then is just the line x plus 2, but we have to keep that domain restriction from the original function. So this just ends up being a line x plus 2, but there's a hole at x equals 4. Okay, that's what happens here in this function. We can cancel those out and just get a line, but we have to keep that original domain restriction. So our graph then, if we go down to part D, we can easily sketch out our graph. Okay, we know this is just going to be the line x plus 2. So I'm going to be going through 2 here. But I know that at 4, there's going to be a hole. And we determined that the x value of 4 was not part of the domain. But what we did figure out in parts B and C, okay, was that we were approaching a value of 6, a y value of 6 from both sides. Therefore, the limit as x approaches 4 is equal to 6. And we did that without the graph, right? We figured that out before we looked at the graph. Okay, we just figured that out with a table this time. And so we're really doing the same thing as we did on Friday, just using a different method. Okay, we did it with a table. And so, I guess that's pretty much everything on this little discovery. Okay. We talked about really all the answers here on the back. And we talked about why the graph's linear here. We know the symbolic form, right? So down here, the limit as x approaches 4 from the left is 6. The limit as x approaches 4 from the right is 6. Therefore, the two-sided limit exists and is 6. So any questions about this idea from a table? Okay, there'll be a couple of questions on the homework. Okay, I think one where you have to create your own table just like that, and then another one where you're given a table and you just have to figure out the limit. Okay, so any questions on finding limits from tables? Okay. Better than graphical? Alright. Yeah, I mean, if you like this way better, sure. I think graphical is a lot easier. If you like this way better, more power to you. Alright. Then, today we're also going to take a look at limits algebraically. Right? So, creating a table like that does take a little bit of work. Okay? So, sometimes it's going to be easier to figure these things out algebraically. Let's start with an easy one. Let's say the limit as x approaches 2 of 2x plus 3. Okay, so a lot of times when you see limits written out, instead of saying f of x, they'll just actually put the whole function. Okay, so the limit as x approaches 2 of 2x plus 3. Okay, now if we just think about this function, we know that that's just a line. Right? Are there any domain restrictions on that? No, right? It's just a line. Domain is all real numbers. So I know that no matter what value I choose, what x value I choose to approach, the function is going to be equal to the limit. Right? This is just a continuous function. It's just a line. So what I can do here, I can just plug that value of 2 into the function. Right? So I can just say this limit is going to be 2 times my x value of 2 plus 3. The limit of 2x plus 3 as x approaches 2 is equal to 7. Right? The goal, whenever we're thinking about these algebraically, is going to be to get our function to a point where I can just plug this in. Okay? That'll make more sense here in a minute. Okay? In this first example, we were already to that point. Okay? I can just plug 2 right into this function, and I get a value. Okay? So that's the first thing that we always want to try. Okay? So if I give you something like this, right? The limit of x squared minus 7 as x approaches negative 3. And we've got a quadratic here. Are there any domain restrictions on this quadratic? No. And its domain, again, is all real numbers. So if there are no holes, there are no asymptotes, there's nothing weird going on with this function. If I plug in negative 3, I get a value. Okay, so what is the limit of x squared minus 7 as x approaches negative 3? 2, right? We would get 9 minus 7. We get 2. Okay, so in both of these cases, the limit just equaled the function value, right? I mean, and you can think about this graphically, right? 2x plus 3 is just this line that looks like this. So at x equals 2, I'm approaching a value of 7 from both sides. And this one, if we think about it graphically, x squared minus 7, this looks something like this. So as x approaches negative 3 over here, I'm approaching a y value of 2 from both sides. Now, these ones are super easy, right? If you've got nice functions, all we have to do is plug in this value and we get our limit. Now, what gets a little bit hairier is if we come across something like this. Okay. Here, if I plug in 2, I get 0 over 0. Okay. Not good. Okay. That doesn't mean, though, that the limit doesn't exist. Right? We talked about on Friday, there are some scenarios where the limit does not exist. That is possible. But in something like this, if we just plug 2 in and we get 0 over 0, that does not automatically mean the limit doesn't exist. What we want to do is try to algebraically manipulate this somehow to get to a point where I can plug in this value. Okay? So this one is actually pretty similar to the example that we did on that sheet. So how could I algebraically manipulate this to get it to a point where I could plug in 2? Yeah, so this top factors, right? How would that factor? Right, it's the difference of squares. So x plus 2, x minus 2. Oops, here we go. X minus 2. X minus 2's cancel. And now, this looks like one of these problems up here. Right? Now all I have is the limit, let me rewrite this, the limit as x approaches 2 of x plus 2. Okay, and now I am to a point where I can plug this value in and get out a real answer. Okay. And that would be 4. And we get 2 plus 2 is 4. So the goal is to get our function to a point where I can plug in this value. Sometimes it will already be there. Sometimes all we'll have to do is plug in the value so that the function will give. Sometimes we'll have to do a little bit of algebra. So in this case, we had to do some algebra. Let's see. How about x approaches 3, x squared minus 1 over x plus 1. So what's the first thing that you want to do here? Right. First thing you want to do is plug in your value. Right? In this case, I don't have to do any algebra. If I plug in 3, I get an answer. I get a real number. Right? It's only when you plug in that value and you don't get a real number. Right? Like in this case, when I plugged 2 in, I got 0 over 0. Then I had to do some algebra. In this case, right, even though this function looks really similar to this one, if I just plug in 3, I get a real number. Okay? If I plug in 3, what do we get? 8 over 4. Right? I didn't have to do any algebra at that time. It's only when we plug in this value in question we get something up. So the first thing that we want to do is plug in the number. Yeah. And if we get out a real answer, that's it. That's the limit. If we don't, though, that doesn't mean it doesn't exist. Like in this example here, right, when we plugged in 2, we got 0 over 0. That didn't mean the limit doesn't exist, though. We just had to do a little bit of algebra. Yeah. Right? There are instances that we'll look at later, though, where it just doesn't exist. Okay, but for today, we're just going to look at the examples where they do exist. Okay, where first thing you want to do is try plugging in the number. If that doesn't work, try doing some algebra. Okay, so the biggest strategy that we're going to look at today is factoring. Okay, we'll look at a few examples probably tomorrow where we use conjugates and some other algebraic tricks to manipulate functions to get them to a point where we can plug in the number. Okay, but for today, all we're going to think about is first thing I want to do, plug in the value. Right? If that works, that's my limit. Right? That's the situation where the value of the function is included at that point. Okay? In this case, okay, this is where there's a hole in the graph, but the function is still approaching the same value from both sides. Right? Even though there's a hole there, we're still approaching the same value from both sides. Any other questions on this idea?